Hello there and welcome back to The Sleepless Scientist. Tonight you're in motion. The world around you blurs, the wind shrieks past your ears, and the lines on the highway flicker like film reel frames. You're doing 70, maybe 80, definitely faster than the posted limit. But who's counting? Certainly not time, or is it? Because unbeknownst to your sleepy brain and the empty coffee cup rattling in the cup holder, something subtle and peculiar is happening to your dashboard clock. It's ticking, just a little bit slower than the same clock in your kitchen. It's not broken, it's physics. You probably won't survive this, by the way. Not because of a crash, but because time might slowly stretch you out of sync with the universe. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And let me know in the comments, where are you listening from and what time is it for you right now? Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You accelerate. And though the leather seat stays stubbornly stuck to your back and your Spotify playlist shuffles through too many sad songs, you're already in the realm of time dilation. Not the dramatic kind. No, you're not aging slower just because you're late for work, but the principle is alive. Even at highway speeds, the rules of time begin to loosen. The effect is microscopic, sure, but it's measurable. In fact, in the 1970s, scientists flew atomic clocks on airplanes and compared them with clocks that stayed on the ground. The ones in the air ticked ever so slightly slower. The Earth's spin and the plane's motion gave them a minuscule time advantage. It's the same with you right now, barreling down the interstate in your faithful clunker. You're shifting through time in a way no ancient human ever could. A caveman never time-travelled by going 80 miles per hour. You just did. What you're feeling is special relativity's warm-up act. Einstein's theories might sound complicated, but the core idea is simple enough. The faster you move, the slower your clock runs relative to someone standing still. But here's the twist. You never notice the difference. To you, your own clock always ticks normally. It's only from the outside, from the perspective of someone else, that time begins to warp. Historians still argue whether Galileo ever considered the strange implications of time in motion, but he certainly paved the path for Newton and later Einstein. Galileo's relativity principle said the laws of physics are the same whether you're on a moving ship or standing on land. But Einstein went a step further. He showed that not just the laws, but time and space themselves stretch and twist based on how you move. So back to your speeding self. You're basically in your own little bubble of slightly tweaked time. It's not enough to shave years off your life or make you younger than your spouse, but it's there. Every single speedometer needle, every race car, every satellite is flirting with Einstein's equations, whether they know it or not. Speaking of flirting, let's talk about the GPS in your car. That helpful little voice telling you to turn left in 500 feet only works because the system constantly accounts for both general and special relativity. The satellites are moving fast and orbiting high above Earth, where gravity is weaker, so their clocks, tiny, precise atomic clocks, tick at a different rate than the ones down here. If those relativistic adjustments weren't made, your GPS would drift by about 10 kilometers a day. Imagine asking for directions to Taco Bell and ending up in a cornfield. And yet, despite all this, your body doesn't feel any different. Your breath fogs up the window just the same. The engine hum is as soothing as ever. Maybe your arm's a little sore from holding the wheel, or your foot's cramping from trying to maintain the cruise control sweet spot. That's the strange poetry of time dilation. Something so profound, so universe-bending, has the decency to be utterly invisible in your day-to-day life. The first experimental confirmation of time dilation came from particles called muons. These high-speed cosmic ray particles zip into our atmosphere and decay in microseconds. At least they should decay that fast. But more of them reach the ground than expected. Why? because their internal clocks are ticking slower as they hurtle toward Earth. It's not science fiction, it's a laboratory measured fact. And here you are in your car, unknowingly replicating the same principle. Your body is still subject to Newtonian friction, coffee-induced jitters, and questionable late-night food decisions, but your atoms, your very molecules, are part of a space-time ballet. Quirky fact of the night. In the 1990s, someone proposed building a time dilation racetrack, a circular particle accelerator big enough to put a human inside, letting them orbit at near-light speeds. It was more conceptual art than science plan, but hey, who hasn't wanted to ride a roller coaster that also makes you younger than your friends? Of course, that's not what your 2014 Corolla is doing. It's aging normally. You're aging normally. But the takeaway here is this. Movement isn't just motion. Movement, in Einstein's universe, is a ticket to a slightly different experience of time. If you could measure your speed perfectly, even on this mundane drive to pick up paper towels, you'd notice the tiniest discrepancy in how many ticks your heart counted versus someone standing still. The faster you go, the more dramatic the difference becomes. But it starts now, with you, speeding gently into the arms of warped time. And as your headlights wash over the reflective road signs and the sky thickens with a galaxy's worth of ancient light, just remember, you're not just passing through space, you're bending time, 1 mile at a time. You're still driving. The road stretches like taffy beneath your tyres, and the sky is dark enough now that stars are starting to twinkle above the distant treetops. You glance up for just a moment, and in that moment, everything slows down. Not in a poetic way, in a very literal, very Einsteinian way. Let's rewind, not the tape, but your understanding of time. You imagine yourself on a train, not a rickety commuter ride with sticky floors and bad Wi-Fi. This one is sleek, futuristic, humming quietly as it slices through the countryside at unimaginable speeds. Outside, someone stands on the platform watching. A bolt of lightning strikes at both ends of the train. You, sitting at the centre, see the bolts at the same time. But the person outside, they see the front bolt first. Why? Because the train is moving forward into one flash and away from the other. Here's the kicker. You're both right. Einstein's brilliance wasn't in building on someone else's equations. It was in flipping a philosophical table. He showed that simultaneity, the idea that two things can happen at the same time for everyone, everywhere, is an illusion. That's a bedtime thought worth losing sleep over. Reality is not consistent between observers. Time is relative not just in theory, but in the very fabric of experience. Historians still argue whether Einstein got this exact scenario from a train ride near Bern, Switzerland, where he worked at a patent office. What we do know is that he famously imagined these sorts of setups, moving clocks, beams of light, fast-moving frames of reference, not with data, but with thought, pure mental gymnastics. You, in this moment, are doing the same. Welcome to the mind gym. Take this thought experiment. Imagine holding a flashlight in that moving train. You turn it on and the light shoots forward. To you, it moves at normal speed. But to someone standing outside the train, the flashlight is moving and the light is moving. Shouldn't the light go faster? That's what Newtonian physics would suggest. But Einstein found something weird. No matter how fast you move, the speed of light remains the same for everyone. This single weird thing breaks time itself. Because if the speed of light is always the same, then something else, time, has to bend to make that math work. Time must slow down for moving observers, because otherwise, two people would measure different speeds of light, and the universe absolutely hates inconsistency. Let's get personal. Imagine you're running beside a beam of light. Not jogging, more like defying the energy crisis sprinting. According to relativity, The light still races away from you at the exact same speed as it would if you were standing still. That's like playing catch with someone who throws the ball at 100 miles per hour, and no matter how fast you run, it always zips away from you at exactly 100 miles per hour. Creepy. And that forces the universe to twist time and space to make that situation work. Quirky sidebar. The idea of universal time, everyone's clock ticking together like synchronized metronomes, was partly fueled by the need to run railroads efficiently in the 1800s. Before that, every town had its own local time based on the sun's position. Trains kept crashing because 12 o'clock wasn't the same from one town to the next. Ironically, our need to control time helped us discover we never really controlled it to begin with. So back to your imagined train. 2 lightning bolts, 1 confused passenger. That thought experiment led directly to what Einstein called special relativity. The idea that the laws of physics are the same in all inertial, non-accelerating frames, and that the speed of light is a constant. Everything else, time, space, simultaneity, must bend to keep those 2 postulates true. This isn't just ivory tower theory. You live with this truth. Every time you watch a space shuttle launch, you're witnessing clocks slow down. Every time an astronaut comes home, their wristwatch ticks out of sync with the one they left behind. This isn't because their watch malfunctioned. It's because they lived time differently. You start to see the unsettling implication. Time isn't a universal flow like a river. It's more like a winding path, sloping differently depending on how fast you're walking, or flying, or orbiting a planet at ridiculous speeds in a tin can held together by heat-resistant tiles and ambition. Even something as mundane as watching a satellite move across the sky should make your brain tingle a little now. That satellite is moving fast enough and high enough to exist in a measurably different frame of time than you, and yet it still sends signals that let your phone tell you where the nearest gas station is. Welcome to the dance of clocks. Now there's another layer, space itself. If time can stretch, so can space. In fact, they're not separate. Einstein's insight was that they're part of the same thing, space-time. When you move through space, you alter how you move through time. It's a cosmic trade-off. You can't have both. Perfect stillness in space and perfect consistency in time. The universe won't allow it. Fringe detail for you. There's a theory, though not widely accepted, that somewhere in the deep mathematical trenches of string theory and multiple dimensions, there might exist frames of reference where you can trick space-time into letting you see 2 moments at once. It's speculative, it's fringe, but it does make you wonder whether those déjà vu moments are more than just brain glitches. So here you are, pulled over now maybe, or slowing to a crawl in a 25-mile-per-hour school zone, and even this gentle deceleration is a form of rebellion against time dilation. You're returning to the shared experience of everyday time, boring, pedestrian, Newtonian time, but for a while you are bending the universe's most sacred rule. Let's end on a small, stubborn fact. Einstein's theories didn't immediately earn applause. Many of his peers found them baffling, even arrogant. After all, he was saying that centuries of physics needed rewriting. Yet the math held. The predictions worked. And here we are, in a world that orbits, navigates, and calculates thanks to time being squishy. And you? You're no longer just a sleepy driver on a long road. You're someone who's dipped a toe into the relativistic deep end. The train, the flashlight, the lightning bolts, they live in your mind now, whispering quietly every time your car accelerates. You're moving again, this time not in a car or on a train in your mind, but deeper into the realm where speed starts doing some truly weird things to time. You're not just coasting anymore. You've hit the throttle of thought, pushing past the quiet playground of Einstein's thought experiments and into the fast lane of special relativity itself. Let's go ahead and imagine you're on a ship, not the ocean kind, but a sleek, silent spacecraft slicing through the black ink of space at an obscene fraction of the speed of light. We're talking 90%, maybe 95% if your nerves can handle it. From your seat, strapped in and surrounded by softly humming instruments and some suspiciously flavourless astronaut paste, everything inside your cabin feels normal. Time ticks by steadily. Your playlist runs at the same BPM. You even do your little skincare routine before sleep because, hey, your future self deserves it. But back on Earth, something very different is happening. This is where the full power of special relativity slams into view. As your speed increases, the passage of time outside your spacecraft starts to blur and stretch. You're zipping through space, but you're also dragging time behind you like a heavy cape. From Earth's perspective, your onboard clock is ticking slower. If you checked in regularly via video feed, with a serious delay thanks to distance, Mission Control would notice something bizarre. Your voice is slightly lagging. Your hands move more slowly. Your speech patterns are just a smidge off. But to you, it's all totally normal. The weirdness only shows up when frames of reference start comparing notes. And here's where the math kicks in. Don't worry, we won't dive into equations, just the vibe. The closer your speed gets to the speed of light, the more dramatically time slows down for you compared to someone stationary. This isn't a glitch, it's the core of reality. Let's say you're cruising at 99.5% the speed of light on a deep space mission that, from your perspective, lasts about 5 years. You're eating vacuum-sealed spaghetti and sending the occasional space selfie to your cousin back on Earth. But when you return home, surprise, she's a grandmother now. You've aged 5 years, but 20, 30 or more may have passed on Earth. This isn't a plot twist, it's physics. It's called time dilation, and it's baked into the very structure of space-time, as described by Einstein's special relativity. The faster you go, the slower your time flows relative to someone else's. It's not just your heart rate or your sense of fatigue. It's your biological clock, your perception of now, your every breath, slowed down in the eyes of the universe. Historians still argue whether the 1905 paper in which Einstein laid out this theory on the electrodynamics of moving bodies was fully understood by the scientific community at the time. Some say it was overlooked for years, overshadowed by his more famous E=mc² formula. Others claim the brilliance was obvious to anyone paying attention. Either way, the implications were massive. Now imagine you had a clock on your spaceship and another identical clock left behind on Earth. You sync them perfectly before departure. When you return, your clock reads 5 years. The Earth clock is ticking closer to 30. That's not because someone messed up the batteries, it's because you live time differently. Your reality forked the moment you hit relativistic speeds. Quirky fact break. One of the earliest attempts to explain this effect to the public came in the form of a children's story. In the 1910s, an illustrator named Max Fleischer, yes, the guy behind Betty Boop, created an animated film where a boy travels near the speed of light and returns to find his parents old and grey. Kids were horrified, which is to say, it worked. But here's where it gets even stranger. Time doesn't just slow down, it contracts space as well. The faster you go, the more the distance between you and your destination shrinks, from your point of view. So that star system 20 light years away? At near light speed, you could get there in just a few years of your time, because the universe squashes the distance for you. You're not breaking the speed of light, but the universe itself is helping you cheat. Imagine this like a treadmill in reverse. While you run forward, the belt beneath you shortens the track. You run hard, but somehow arrive faster than seems possible. You didn't cheat, you just bent reality to get there. Fringe theory moment. Some physicists speculate that at extreme relativistic speeds, your perception of cause and effect could start to behave oddly, maybe even letting you see into events that haven't fully unfolded from another frame's perspective. Again, speculative stuff, but it hints at just how strange the edges of time dilation can become. The important thing? This isn't theoretical anymore. We've already observed time dilation in action. Remember the Muons from earlier? Those high-speed subatomic particles rain down from space, created when cosmic rays hit the upper atmosphere. They live incredibly short lives, microseconds in fact, but because they travel so fast, near light speed, they experience time so slowly that many survive the trip to Earth's surface. From our perspective, it's miraculous. From the Muons' perspective, they're just falling normally. You're not a Muon, probably, but you share their fate in principle. The faster you move, the more time you carry differently. Your internal biological processes don't know they're running slower than Earth's timeline, but the math doesn't lie. There's a sadness tucked in this reality. Imagine you're the astronaut returning home decades later. Friends are older, the cities have changed, the culture is unfamiliar. You've only been gone a few years by your count, but the planet has kept spinning without you. Time dilation then becomes more than physics. It becomes emotional, a kind of built-in loneliness, a cost of speed. Still, there's something beautiful here too. The idea that time is not a straight, uncaring line. It's soft, it bends, it makes room for movement and momentum. You're not stuck in time, you're surfing it. So the next time you stare out the window of a plane, or glance up at a satellite tracking overhead, remember this. Motion isn't just movement. It's a whisper to time that says, I don't have to follow your rules exactly. And time, begrudgingly, listens. The ship hums beneath you, a low, comforting rumble like a cat purring beside your ribcage. You're in orbit now, not around a planet but around a concept. Time, twisted. You drift near the speed of light, comfortably encased in your spacecraft, staring into the endless abyss of stars that are both ancient and current, depending on who's asking. Outside your window, the universe continues its business. Stars burn, comets swing, and distant galaxies shine with light that's already millions of years old. But for you, time has taken on a new rhythm. You're no longer just riding it. You're stretching it, manipulating it with nothing but velocity and mass. Let's run a scenario. You're an astronaut on a high-speed journey to a star system 20 light-years away. If you were standing still, the math is simple. Light takes 20 years to get there, so you should take longer. But you're not standing still. You're moving at 99.9% the speed of light. From the perspective of people on Earth, you're still taking around 20 years to get there. But from your seat, snuggled into the cockpit with a freeze-dried taco and an audiobook about loneliness and space, the trip only lasts about a year. 1 year, that's all you feel. That's all your body ages. That's time dilation in full swing. The faster you move, the shorter the trip feels to you. Space contracts. Time slows. It's like the universe itself is rolling out a shorter path just for you. And when you turn around and come back, the same thing happens again. You've only aged 2 years, but Earth has aged 40. It's a situation known as the twin paradox, though we'll explore that in more depth later. For now, what matters is that from Earth's point of view, your internal clock was crawling. Everything you did, eating, blinking, aging, was in slow motion. You felt fine. They saw you stretch out across time like taffy. Historians still argue whether this paradox was intended to be a real situation or just a thought experiment. Some insist it's a mental puzzle with no practical application. Others point out that the principles are already in use today, in satellite tech, particle accelerators, and cosmic observations. Whatever the original intent, we now know it's real physics, not fantasy. In fact, modern astronauts experience tiny amounts of time dilation every time they go to space. Not enough to notice without a calculator, but measurable. That's the beauty and curse of relativity. It doesn't wait for dramatic sci-fi scenes. It's always on, always working, even when no one's paying attention. Let's talk about velocity again. As you approach light speed, time dilation doesn't just increase linearly, it ramps up dramatically. At 50% of light speed, the effect is noticeable but small. At 90%, it's significant. At 99.99%, time nearly freezes. To outside observers, you become almost motionless in time, a living statue sailing through space. But from inside the ship, the coffee's still warm, the audiobook's still annoying, and you're counting the same heartbeats as always. Quirky side note. During the 1960s, NASA considered whether extremely fast-moving deep space probes could be used as time capsules, taking biological samples far into the future. The idea was to launch frozen embryos at near light speed and let them arrive hundreds or thousands of years later, aging just days en route. The ethics were a nightmare, but the physics? Sound. Now here's something deliciously counterintuitive. The faster you go, the more the universe appears to tilt toward you. Literally. Stars ahead of your direction of travel appear to bunch up. Behind you, they stretch out. This is called relativistic aberration, and it's not just a visual trick. The radiation from those stars blue shifts, increasing in energy, while light from behind you red shifts, lowering in frequency, stretching toward invisibility. At extreme speeds, the night sky doesn't look like a starry blanket anymore. It looks like a tunnel of light, a glowing arc that wraps around your destination. The rest of the cosmos fades behind you, warped out of sight. Imagine drifting through a funnel of fireflies at impossible velocity. That's not poetry. That's the visual reality of relativistic travel. And speaking of energy, the faster you move, the more massive you become. Relatively, that is. To an outside observer, your spacecraft requires more and more energy to keep accelerating. This is why you can't ever quite reach the speed of light. You'd need infinite energy to get there, and unless you're hiding an infinite fuel source in your glove box, you'll never quite make it. This brings us to a key point. Light speed is a wall, not a goal. Time dilation ramps up as you approach it, sure, but the moment you reach it, if you could, you'd experience time not just slowly, but not at all. Everything outside your ship would appear to freeze, and that's if you were a massless particle, like a photon. For anything with mass, like you, yes you, the speed of light is a hard boundary. You can flirt with it, get close enough to hear it breathe, but you can't cross it. That's one of the few rules the universe actually enforces without exceptions. Not even rich people get out of this one. Fringe theorists have wondered whether particles moving faster than light, hypothetical tachyons, might experience time in reverse. If they exist, and that's a very big if, they would live backward, born in the future, dying in the past. No evidence for them yet, but the math doesn't forbid them entirely. Which is science's way of saying, we're listening, but also calm down. So you sit in your humming craft, drifting at a speed most people can't fathom, and you realise something. You're no longer bound to the same rules that govern life on Earth. You are aging less. You're travelling farther in less perceived time. You are, in a very literal sense, living in the future. But it's not without a cost. This kind of travel, while cool in principle, isolates you. Everyone you left behind is changing faster than you. Time dilation isn't a party trick, it's a separation. You're not just going somewhere new, you're going somewhere alone. The faster you move, the more the world behind you accelerates away, not physically but temporally, and when you return, if you return, the past will have hardened into history. It's a strange, sobering thought, wrapped in the most beautiful math humans have ever discovered. You can use time dilation to outrun the present, but never without leaving something behind. You're lying in a field now, not a spaceship, not a car, just you and the sky. Above you, Clouds stretch thin and ghostly across the deep blue, and specks of high-altitude glitter drift lazily down. Cosmic rays, atmospheric dust, and something stranger. Muons. You probably don't feel them, but they're there, raining from the sky like invisible snowflakes. They zip toward you at near-light speeds, born from the collision of cosmic rays and atoms in Earth's upper atmosphere. You lie there, blissfully unaware, as a trillion tiny time travelers silently pass through you. They shouldn't be able to. Muons are unstable. From our frame of reference, they live for about 2.2 microseconds before they decay into electrons and neutrinos. That's not enough time to get from the edge of space to your sleepy patch of grass. Even travelling close to the speed of light, they should decay long before reaching the ground. And yet, they do. They reach you in great numbers. Why? Time dilation. From our perspective, these particles are moving fast, relativistically fast, so their clocks are ticking slower. Those 2.2 microseconds stretch out in Earth time, giving the Muons just enough extra seconds to make the journey before poofing into something else. Their lifespan, normally a blink, expands dramatically because they're moving so quickly. But here's the twist. From the Muons' point of view, it's not that they live longer. It's that the distance from the upper atmosphere to Earth's surface shrinks. Remember that whole space contracts as speed increases thing. Muons experience this journey as a much shorter hop. Just a little cosmic puddle jump. Two versions of the same story, both completely correct. Welcome back to Relativity, where truth depends on who you ask. The Muon shower isn't a rare event either. It's happening constantly. Right now, Muons are streaming through your body, through buildings, oceans, even mountains. They're useful little spies. Scientists can use them to probe pyramids, volcanoes, and even collapse caverns, like X-rays from space. But back to the field. You're lying there, unmoving, while those Muons are screaming through space-time at absurd velocities. In this moment, you're the stationary observer. Your watch ticks normally, your breathing syncs with the swaying grass. But for the Muons, time is syrup thick. Seconds crawl, distance collapses. This is the first solid experimental proof of time dilation in nature. Muons arrive when they shouldn't, because time itself behaves differently for them. We didn't discover this in a lab. We discovered it in the sky. Historians still argue whether the 1930s experiments that detected these Muons were truly understood in terms of relativity, or if they were simply anomalies to explain later. But by the 1940s, the connection was undeniable. Time dilation wasn't just some theoretical oddity anymore. It was raining down on us, literally. And the experiments got even better. In 1979, scientists built towers and measured Muons at the top and bottom, comparing their decay rates. Sure enough, the ones moving faster lived longer, just as Einstein predicted. No loopholes, no fudge factors, just cold cosmic proof. Quirky detail? There's a small group of amateur physicists who believe they can feel Muons. No solid evidence, of course, but some swear by a faint tingling or warmth during heavy cosmic ray showers. More likely, it's imagination or static. But still, it adds to the charm of these silent visitors from the stars. And here's something slightly mind-bending. Muons are born high in the atmosphere, in a place we could technically reach by balloon. But their existence is tied to galaxies billions of light years away. The cosmic rays that create them? Those are fired across the universe, sometimes from exploding stars, sometimes from even stranger things we barely understand. Quasars, magnetars, maybe even the whispers of dark matter. In that sense, every Muon is carrying ancient energy. Every time it strikes your shoulder or glides through your phone, it's leaving a fingerprint from the dawn of time. And because of time dilation, that fingerprint takes its sweet time getting to you. Let's flip the script. If you're a Muon, born screaming through the sky at 99.9% the speed of light, You'd blink into existence, watch Earth hurtle toward you, and then decay just in time to say hi to a curious physics student at sea level. You wouldn't feel like time was crawling. You'd feel normal. You wouldn't suspect anything strange was happening. From your view, your life would play out in a proper sequence, nothing rushed or slowed. But from our view, you just pulled off a time-based miracle. This duality, normalcy inside, distortion outside, is the core of relativity. You, moving at high speeds, always feel normal. But everyone else watching you disagrees. It's like being at a party where you think your dance moves are fire, but every bystander sees slow-motion chaos. The Muon paradox shows us that time dilation isn't science fiction. It's already embedded in nature, and it doesn't require warp drives or fancy tech. Just speed. Raw, relentless, unbending velocity. Here's another layer. Muons aren't alone. Every subatomic particle flying through the universe at high speed experiences similar time dilation. Particle accelerators like the Large Hadron Collider rely on this fact. They whip protons around at nearly light speed, and if time didn't slow down for those particles, we wouldn't be able to study them long enough to learn anything. They just disintegrate mid-spin. Instead, thanks to relativity, they hang on just long enough to leave trails we can track. Every equation, every collider experiment, every Nobel Prize tucked inside particle physics owes a tip of the hat to time dilation. And you're still in the field. You open one eye, yawn, check your phone. Still the same time as before, more or less. But above you, whole lifetimes have played out. Subatomic dramas, decay, birth, annihilation. Each one telling a story about time that contradicts everything you were taught in elementary school. Because time doesn't just tick. It stretches. It curls. It runs differently depending on where and how fast you are. You might not be able to feel the muons, but next time you watch a meteor shower or see a shooting star blaze across the sky, remember that the same cosmic forces are touching your skin, whispering secrets from the farthest corners of the universe, slowed down just enough for you to hear. Your phone buzzes gently beside you, snapping you out of your cosmic Muon meditation. You glance at the screen, maps, GPS, a little blue dot moving slowly across the grid, a turn in 300 feet, then another, then home. The voice chirps pleasantly. Everything seems so simple. But here's the truth. That quiet little voice only works because of a constant battle with time. You're holding one of the most advanced pieces of relativity-powered tech in your palm, and you didn't even have to sign up for a physics degree to use it. GPS, that everyday marvel we treat like digital magic, actually runs on Einstein's rules. Without corrections for time dilation, the system would fail. Not in a few months, not in a few years. It would be completely unusable within minutes. Let's break it down. The global positioning system relies on a network of satellites orbiting the Earth at around 20,200 kilometers, or 12,550 miles, above the surface. These satellites aren't just passive space junk. They're atomic clock-carrying speed demons, zipping through orbit at about 14,000 kilometers per hour, and they each carry ultra-precise timing devices that synchronize with your phone to determine exactly where you are. That location. It's all about timing. Your phone listens to signals from multiple satellites and calculates how long each signal took to reach it. Multiply that time by the speed of light, and boom, you get distance. With enough satellites, you can triangulate your exact location down to a few meters. Simple, right? Except it's completely wrong if you ignore relativity. First, there's special relativity. The satellites are moving fast relative to you, down here on Earth. That means their onboard clocks run slower than yours. Not by much, about 7 microseconds per day, but still enough to cause trouble. Then toss in general relativity. Because the satellites are in a weaker gravitational field than we are, being farther from Earth, their clocks run faster. That adds another 45 microseconds per day in the opposite direction. Do the math, and the total net effect is that the satellite clocks run about 38 microseconds faster per day than clocks on Earth. Doesn't sound like much? It is. If uncorrected, this time offset would lead to positioning errors of up to 10 kilometers per day. You'd be told you're at a lake when you're at a library, or in another state entirely. So engineers do what engineers always do. They plan for the weirdness. They build those relativistic adjustments into the satellites from the start. The clocks are calibrated to tick slower at launch, knowing they'll tick faster once in orbit. It's like giving your watch a head cold so it works properly in zero gravity. Historians still argue whether the designers of GPS fully understood the implications of relativity from day one, or if it was just a brilliant post hoc patch job. Some accounts suggest early engineers resisted Einstein's equations, worried they'd complicate things. Others say they embraced it enthusiastically. What's clear is that without time dilation corrections, your Maps app would be little more than a cartoon compass. Quirky detour for you. In the early 2000s, a group of high school students replicated GPS relativistic corrections as a science fair project. They launched small-scale simulations using backyard antennas and Raspberry Pi computers, confirming that even at tiny altitudes and low speeds, the adjustments still mattered. One judge called it the most casually accurate space-time project I've ever seen. So the next time you tell your phone to find nearest sushi, remember, 4 or 5 satellites just compared clocks in orbit, adjusted for velocity and gravity, compensated for time dilation, and sent you coordinates, all within a few milliseconds. You're living in the future, and it's brought to you by a combination of rocketry, atomic physics, and one dead Swiss patent clerk. Let's also take a moment to admire the clocks themselves. The satellites use atomic clocks, usually based on the vibrations of cesium or rubidium atoms. These clocks are ridiculously precise, losing or gaining just 1 second over millions of years. And yet, without Einstein's corrections, even those clocks would drift out of sync. The universe is unforgiving when it comes to speed, and it's not just GPS. Every satellite-based system, weather monitoring, telecommunications, military targeting, requires relativistic corrections to stay accurate. Without time dilation, even satellite TV would drift out of sync. Imagine your favourite show's audio and video slowly falling out of alignment, all because the universe has trust issues with your clocks. From your earthbound perspective, time feels stable, predictable, but 20,000 kilometers up, every second is a negotiation. Every tick is filtered through layers of velocity, gravity, and space curvature. It's cosmic bureaucracy. Here's something to chew on. Your phone's internal GPS system can also account for relativistic Doppler effects. When a satellite is moving toward you, the frequency of its signal shifts slightly. It's not quite the same as hearing a siren change pitch as it rushes past, but the principle holds. Your phone detects that shift and adjusts accordingly, silently, instantly, and without asking for applause. And yet, we give GPS so little credit. We get annoyed when it's off by 5 feet. But it's coordinating signals between your tiny rectangle of glass and machines flying through warped space-time at thousands of kilometers per hour. Cut it some slack. Fringe tidbit. There's a semi-serious proposal floating in tech circles to one day replace GPS with a network of pulsars, those hyperdense spinning neutron stars that emit regular radio pulses. Their timing is so precise they're like natural atomic clocks scattered across the galaxy. It would be the ultimate relativistic navigation system. We'd call it XPS, EXTRATERRESTRIAL positioning system. No joke. But for now, GPS reigns, quietly solving Einstein's puzzles every time you look for the nearest coffee shop. As you walk, or drive, or stumble your way back toward home, maybe let the realization settle in. you're tracking yourself across curved space-time. Your location is the product of relativistic geometry, satellite mathematics, and atomic ballet. You're not just a blue dot on a screen, you're a living testament to the fact that time is fluid, and we figured out how to surf it, at least a little. So the next time you miss a turn, don't curse your phone. Thank it for doing impossible math faster than your brain can blink, and for bending time just enough to help you find your way. You're standing in a white hallway. Fluorescent lights hum softly above. A calendar hangs on the wall, its pages fluttering slightly in the breeze from a distant vent. There are 2 chairs. In one, you sit. In the other, your twin. Identical in every way. Same face, same crooked eyebrow, same bored expression. But not for long, because in a moment one of you is about to board a spaceship. This is the twin paradox, and it's not a riddle or a trick of words. It's a fundamental result of special relativity, and it still manages to mess with people's heads over 100 years after it was first proposed. Here's how it goes. You and your twin are the same age, born 1 second apart. Let's not get technical. But for the sake of science, your twin gets volunteered to take a high-speed trip into space. They board a ship capable of approaching light speed, zooming out to a distant star system and returning after what, to them, feels like a short trip. Maybe a year or 2, maybe 5. They were reading, doing experiments, eating astronaut soup, occasionally waving at Earth through the rearview monitor. Meanwhile, you stayed home, you paid taxes, you binged all 12 spin-offs of the same cooking show, you grew older. When your twin finally steps out of the ship, they look almost exactly the same as when they left. But you're decades older. Same DNA, same birthday, different futures. This is time dilation in full effect. The faster your twin moved, the more slowly time passed for them, from your perspective. They've skipped ahead in a way. Not backward, not forward in the sci-fi sense, but forward through less time. They've aged less, lived fewer seconds, taken a shortcut through the 4th dimension. And here's the fun part. This isn't just a mind game. NASA ran a real-life version of this when astronaut Scott Kelly spent nearly a year aboard the International Space Station, while his identical twin Mark Kelly remained on Earth. The differences in aging weren't dramatic, just a tiny tick, a fraction of a second. But they were measurable. With sensitive enough instruments, that tick matters. It was the twin paradox, not just imagined, but happening in low Earth orbit. Historians still argue whether the public truly understood the implications of the Scott Kelly mission when it happened. Most headlines focused on genetics or muscle loss, not time dilation. But the truth remains. For the first time in history, we had a twin return home slightly younger, not just biologically, but relativistically, than the one who stayed behind. So why is it a paradox? That's the confusing part. After all, shouldn't both twins think the other is aging slower? That's what relativity seems to say. Motion is relative, right? Well, yes, but also no. Here's the key. The twin who went to space had to accelerate. They turned around. They decelerated. They changed frames of reference. That breaks the symmetry. While both twins think they're still, and the other is moving during the cruising part, only the traveller experiences acceleration. That change in velocity, that moment of turning around, is what makes their clock run differently when the two are finally reunited. Relativity doesn't blink. It keeps track of every tick. Quirky detail. Some scientists have written full-blown science fiction stories based on this paradox. One version involves a group of twins sent in opposite directions at near-light speed to colonize the stars, each aging slower than the civilization they left behind. When they all return a century later, Earth has moved on. Entirely different cultures, languages, even species dominating the planet. It's part epic, part therapy session. Back in your imagined hallway, the calendar flaps again. Your twin smiles still youthful, and you glance in the mirror. Wrinkles, white hair, and a vague confusion about how to use the latest social media app. This isn't just about physics, it's about experience. Because for your twin, the trip felt normal. They were living every second like you were. But the universe was quietly compressing their timeline, giving them a fast-forward button they didn't even notice. And here's the kicker. You could replicate this yourself in principle. All you need is a spaceship capable of approaching light speed, some serious funding, and a willingness to lose everyone you know. That's the emotional cost of time dilation. Disconnection. You leave the planet, skip a couple decades, and return to a place you no longer recognize. It's not like freezing yourself or jumping through a wormhole. You lived that time, you just lived less of it. And the philosophical implications, they get heavy. What is age, really? Is it just the number of Earth orbits you've witnessed? Or is it the time your body experienced? Is your twin still your age if they've only lived half as many seconds? These questions aren't just for stoners and poets. They're part of a growing field that blends physics with neuroscience and philosophy. There's even debate around whether consciousness itself can stretch across relativistic frames the way clocks can. Historians still argue whether Einstein ever considered the qualia of time travel, what it feels like to be out of sync. Meanwhile, in labs around the world, researchers are using high-speed particles to test the limits of these paradoxes. Muons in accelerators, electrons in magnetic fields, even neutrinos, those barely there ghost particles, are part of the time conversation now. And yet, it always comes back to the twins, the clearest, strangest, most memorable version of time dilation. Two people born at the same moment, one choosing to move fast, the other staying still, and the universe keeping a tally of time so perfect, so unyielding, that their destinies diverge without either one doing anything wrong. So maybe tonight, as you brush your teeth and stare at your sleepy reflection, think about your other self, the one who took the ship, who left time behind, who's still out there, somewhere, younger than you. Because that version of you, that twin you, is already part of reality. You just haven't built the rocket yet. You're drifting now, no longer on Earth, no longer watching clocks tick quietly in laboratories. You're hovering near something darker, something heavier, a black hole, not the kind that gobbles up planets in sci-fi movies with dramatic orchestral scores and last-second escapes. This one is quieter, more patient. You're suspended just above its surface, balanced perfectly at what's called the event horizon, the invisible edge where light itself gives up. 1 inch closer, and not even photons can break free. You somehow float just shy of that point, close enough to feel the universe bend beneath you, and time does something truly bizarre here. To someone watching you from a safe distance, let's say your friend is out there in a spaceship sipping cosmic chamomile, you appear to freeze, not metaphorically, literally. From their perspective, you slow down the closer you get to the black hole's edge. Your movements stretch out like molasses in January. That wave you give them? It takes years, decades even, until eventually you stop waving at all. Not because you're gone, but because time for you has nearly stopped from their point of view. This is time dilation cranked to 11, and it's not caused by motion, like in special relativity. This is the realm of general relativity, Einstein's next-level upgrade. The theory that explains how gravity warps time just as much as speed does. Gravity doesn't just pull on mass, it pulls on time. The stronger the gravitational field, the slower time passes relative to areas where gravity is weaker. Black holes, with their infinite density, create the most extreme example of this effect. You could orbit a black hole for a few hours and return to find centuries have passed elsewhere. Let that sink in. Time doesn't just move differently because you're fast. It moves differently because you're close to something massive. Historians still argue whether Karl Schwarzschild, the German physicist who first solved Einstein's equations to describe black holes, fully understood what he'd unleashed. He derived his solution in the trenches of World War I, scribbling math between artillery barrages. It's poetic, and a bit eerie, that one of the most terrifying ideas in physics was born surrounded by chaos and mud. Back to you, hovering. To you, everything still feels normal. Your ship is intact, your heartbeat steady. You don't feel time crawling. It's only from the outside, from the rest of the universe's point of view, that the distortion becomes extreme. Anyone watching you would think you've become a statue, eternally paused in your final moment before falling in. And the light? Oh, the light. If you were shining a flashlight away from the black hole, your beam would be stretched out, its frequency dropping lower and lower. That's gravitational redshift, light losing energy, falling into deeper and deeper slowness as it tries to climb out of the warped space-time around you. Eventually your light becomes infrared, then microwave, then radio, then nothing. From far away your glow disappears. You become invisible. But here's the kicker. You're still alive, still moving, still experiencing time normally inside your little bubble. But the rest of the universe has moved on. If you try to radio Earth, your message might arrive long after humanity has stopped listening, or existed at all. Now let's say you do cross the event horizon. What happens next depends on what kind of black hole you're near. Some theories say you're torn apart by tidal forces. Spaghettification it's called, because of course scientists gave it a ridiculous name for such a horrifying fate. But if the black hole is large enough, you might not feel anything at first. No sudden crunch, just more time slipping away. The problem is, once you're past the event horizon, you're committed. There's no turning back. Not because your ship isn't strong enough, but because space itself is curved inward. Every direction leads deeper in. Even if you try to fly away, you're only flying further in. It's like trying to escape a whirlpool by swimming toward the center. Quirky fact? There's a hypothetical concept called a white hole, the opposite of a black hole. Instead of sucking everything in, it spits everything out. Violently. Constantly. Think cosmic reverse vacuum cleaner. They've never been observed, but the math allows them. Some theories even suggest that what goes into a black hole might come out of a white hole somewhere else, maybe even in a different universe. That's a conversation for another sleepy night. Back to time. There's a scene in that space movie, you know, the one with the bookshelf and the overly intense organ soundtrack, where astronauts spend a few hours on a planet orbiting a massive black hole, only to return and find that 23 years have passed for their crewmate. That scene is inspired by real physics. It's exaggerated, sure, but the concept is valid. Near the event horizon of a black hole, time is so distorted that you can live a short afternoon while decades, even centuries, slide by elsewhere. Think about that. Really think about it. You could spend a lazy weekend near a black hole and return to a world that no longer recognizes you. Maybe the continents have shifted. Maybe your favourite band finally released that album. Maybe languages have changed, people have moved on, entire civilizations have risen and fallen, and you were gone for what felt like a blink. Time dilation, when combined with gravity, becomes a time machine of sorts. Not one you can program or control or use to save Lincoln, but a natural one-way time machine. All it takes is courage, shielding, and a willingness to leave behind everything you know. And the strangest part? You wouldn't notice the difference until you tried to return, until you compared your watch to the universe's. You might think time is your loyal companion, a thread connecting every second to the next. But out here, at the edge of cosmic collapse, you realize the truth. Time is fickle. Time bends. Time waits for no one. Except, maybe, you. As you hover above that impossibly dense point of no return, You look around and realize something beautiful. You're standing at the very boundary where time itself decides to give up. A place where the ticking of every clock becomes a whisper. A place where relativity doesn't just suggest but demands that time runs differently. And that's the real wonder of black holes. They aren't just scary. They aren't just hungry. They are windows into the fabric of space-time itself, into the relationship between mass, velocity, gravity, and the strange elasticity of time. They are clocks that break all other clocks, and you're right there with them, watching the universe blur around the edges, feeling the minutes stretch like taffy, living slow while the rest of existence rushes ahead. You may never escape this place, but at least you've seen time as it truly is, wild, curved, and untamed. You're back on Earth now, feet planted firmly on a moving, spinning, slightly noisy planet. It feels stable, ordinary, the gravity's familiar, the sky doesn't warp above you, but the strange truth is, time dilation is still happening right here, right now. Not near a black hole, not on a spaceship, on a plane, in a lab, even in your wristwatch. Let's rewind to something seemingly mundane. Commercial air travel. You board a plane, it's cramped, the snack cart is still 5 rows away, and the guy next to you keeps falling asleep on your shoulder. You spend 5 hours flying from New York to LA. What you don't realise is that you've just aged a tiny measurable amount less than your friend who stayed behind at the airport. It's not just speed, it's altitude too. While you're flying, you're moving fast relative to Earth, which slows your clock, thanks special relativity. But you're also higher up where gravity is slightly weaker, which speeds your clock up, thanks general relativity. These two effects push against each other, and depending on how fast and how high you go, one wins out. Turns out, for airplanes, the special relativity effect, slowing due to speed, is slightly stronger than the general relativity effect, speeding up due to gravity. So, yes, your time in the air runs a bit slower, and we can prove it. In 1971, physicists Joseph Haffel and Richard Keating flew atomic clocks around the world on commercial airliners, eastward and westward, up and down. When the clocks returned and were compared with identical ones that stayed put in a lab, they had ticked at different rates. The differences were tiny, just nanoseconds, but exactly what Einstein predicted. Historians still argue whether the experiment's methods were precise enough for definitive proof, but its results have been repeatedly confirmed by more modern and accurate experiments since. Haffel and Keating were just the first to bring relativity to a frequent flyer program. Quirky fact: modern airliners carry high-precision timekeeping instruments to test relativistic effects for education and demonstration. Some airlines even use these experiments to entertain students. Yes, kids on field trips measuring relativistic time shifts. Meanwhile, you're just trying to get your seatbelt to unbuckle. Let's zoom in further to something even more precise than airplane clocks. Welcome to the world of atomic clocks. These are the gold standard of timekeeping, literally. Some of them use cesium atoms, others use strontium or ytterbium, and they can measure time so precisely that they'd lose only 1 second over the entire age of the universe. Now here's the kicker. Even a height difference of just a few centimeters can cause 2 atomic clocks to tick at different rates. That's how sensitive time is to gravity and motion. Stand on a ladder with one clock and leave another on the floor. Come back later. The clock on the ladder will have ticked just a tiny bit faster than the one below. This isn't theory, it's been done, multiple times. You age slightly faster standing than lying down. So yes, if you're taller, you technically age faster than someone shorter. It's okay, let that one settle in. The implication here is mind-bending. There's no such thing as universal time, not even in your own body. Your head experiences time slightly faster than your feet. Your brain is older than your toes. Every second of your life, you're a walking example of time dilation. The effects are microscopic, sure, but they're constant. Now picture satellites again, GPS satellites, orbiting about 20,000 kilometers above us. They're not just moving fast, they're way up in weaker gravity. Special and general relativity both play roles, tugging time in opposite directions, and both effects must be accounted for to make your maps work. But let's make it personal again. You board a plane, you're wearing a high-precision wristwatch, maybe not atomic, but close. You fly from Tokyo to San Francisco. You land. You compare your watch with the one you left at home. The difference is maybe 10 to 20 nanoseconds. That's a billionth of a second. Too small to feel, but not too small to measure. And that's the weird beauty of time dilation. It isn't just for astronauts and science fiction anymore. It's not confined to thought experiments. It's baked into your commute, your GPS, your airline loyalty card, and your very bones. Even a jogger experiences time dilation, slightly. The faster they move, the slower their time runs, relative to the couch potato on the park bench. The difference might be only quadrillionths of a second. But again, it's real. It's measurable. It means something. Fringe detail? There's ongoing research exploring whether athletes who move significantly faster in training environments might experience any measurable biological time shifts. The results so far are tiny, but scientists are curious whether extreme training regimens, coupled with high-altitude conditions, could ever lead to detectable health differences based on relativistic time flow. Probably not, but it's fun to imagine Olympic runners not only outrunning their competitors, but also outrunning time itself. Here's another layer. Particle accelerators, like CERN's Large Hadron Collider, accelerate particles to 99.9999991% the speed of light. At those speeds, time dilation becomes massive. Subatomic particles that usually decay in milliseconds suddenly live for what feels like seconds or minutes, from our perspective. The only reason scientists can study them at all is because their clocks slow down so much in motion. You and I, we live at slow speeds, but even we can't escape the pull of relative time. So the next time you're flying in a metal tube 35,000 feet above the ground, eating pretzels and wondering why your screen won't load, remember, you're actually in a physics experiment, one that proves time itself is elastic, stretchable, personal. And if you ever feel like time is moving too fast or too slow, it's not just your imagination. It might be the airplane, or the Earth's rotation, or the fact that your phone is constantly talking to satellites correcting for time dilation, just so you can find the closest gas station. You're not just a passenger, you're a time traveller. Every second, every flight, every step up a ladder. Time doesn't treat everyone equally. And that's the most wonderfully unfair thing in the universe. You press your hand against the glass. Outside, the stars blur into streaks. You're not in a plane now. You're not on Earth. You're aboard something wildly theoretical. A craft built not by engineers, but by imagination. You're chasing a dream older than physics itself, moving faster than light. You already know the deal. Special relativity says you can't. The equations are clear. As you approach light speed, your mass, at least from the perspective of an outside observer, climbs toward infinity. Your engines groan, your fuel needs spike, and time stretches like a rubber band about to snap. Pushing harder gets you closer, but never quite there. Light speed isn't a finish line, it's a wall, a very shiny, very unbreakable wall, but still, what if? Let's start with the forbidden fruit, tachyons. These hypothetical particles have one defining characteristic. They always move faster than light. They're the opposite of us. They can never slow down to the speed of light. Their math is weird. They'd have imaginary mass, not as in pretend, but as in the square root of negative numbers. Even physicists wince at that. Still, tachyons pop up in string theory and quantum field experiments from time to time, like unwanted guests. No one's ever found one, and if we did, it would break causality. you'd be able to send a message back in time. Cause and effect would collapse. Arguments about who said what first would become literal paradoxes. Historians still argue whether Einstein ever truly believed faster than light, FTL, travel was impossible, or if he just accepted it as a mathematical consequence. Either way, relativity doesn't ban creativity, it just sets the speed limit, but humans hate speed limits. That brings us to something a little less imaginary and a little more speculative, the Alcubierre drive. Named after Mexican physicist Miguel Alcubierre, this concept proposes a loophole. You can't move through space faster than light. But what if you move space instead? Picture a bubble, a space-time capsule. Inside, you're perfectly still. But behind you, space-time contracts, and in front of you, it expands. Like surfing a wave made of the universe itself. This warp bubble could, in theory, carry you across vast distances faster than light would in normal space. To an outside observer, you've travelled faster than light, but you've never broken the rule, because locally you've just been coasting. There's just one problem, or 10. To make it work, you'd need negative energy, exotic matter, something with less than 0 energy density. The kind of stuff that doesn't just not exist, it might be prohibited from existing by the very fabric of reality. Even if it did exist, you'd need ridiculous amounts of it. One early estimate suggested the energy equivalent of an entire galaxy. Still, in 2021, a research team claimed to find a tiny mathematical model of a warp bubble that might not require negative energy. It doesn't transport anything yet, just tweaks space-time on paper, but it's a flicker of possibility, and that's often all science needs. Let's pause here for a quirky detour. In the 1990s, NASA briefly funded something called the Breakthrough Propulsion Physics Project, tasked with exploring FTL travel, anti-gravity, and other physics-defying ideas. It didn't yield warp drives or wormholes, but it did spawn a generation of physicists and engineers who now seriously consider things like vacuum manipulation and quantum gravity engineering. Nerds with ambition, the best kind. Back to FTL travel. Another candidate? Wormholes. Theoretical tunnels through space-time predicted by general relativity. Imagine folding a piece of paper so that 2 distant points touch, then poking a hole through them. That's a wormhole. A shortcut not through space but through the fabric of reality itself. Theoretically, you could step into a wormhole and emerge at the other end faster than light would have gotten there through normal space. Boom. FTL travel, without breaking any speed laws. But again, wormholes require exotic matter to stay open, and even if you could stabilize one, there's a growing suspicion they might collapse the moment anything tries to pass through. Some theories suggest they might exist naturally at microscopic scales. Quantum foam, tiny jittery distortions in space-time smaller than atoms. The hope is that one day we might learn how to enlarge them, like blowing up a soap bubble from a speck of invisible mist. But let's be clear, all of this, warp drives, wormholes, tachyons, it's deeply theoretical. We don't even know how to build a spacecraft that can get to 1/10 of light speed. Right now, our fastest probes, like Voyager or the Parker Solar Probe, crawl compared to what we'd need for relativistic travel. Still, science fiction dreams boldly. In Star Trek, ships warp space with dilithium crystals and matter-antimatter reactions. In The Expanse, drives churn gravity by manipulating fusion pulses. In Interstellar, gravity itself becomes the key to unlocking time travel. These are fantasies, but grounded in physics' fringe edges, and that's where the fun lives. Fringe theory of the day? Some researchers have explored ideas involving entangled particles to create instantaneous communication across light years. Quantum entanglement feels like faster-than-light messaging, but it's not. No usable information travels faster than light. It just looks like it. Spooky action at a distance, as Einstein grumbled. Useful for encryption, not for text to Alpha Centauri. But what if, just what if, we do find a way, not to go faster than light, but to skip the need for light altogether, maybe with dark energy manipulation, maybe with quantum tunneling, maybe with something so alien it doesn't even fit into our current understanding of time, because that's the heart of it really. Time dilation, real, tested, observed, is just the beginning. Once we accept that time isn't rigid, that space can bend, and that gravity isn't just a force but a geometric distortion, we open the door to the truly unthinkable. And maybe, just maybe, the universe is a little more flexible than we thought. So you step away from the window, stars still blur past, light speed still looms ahead, unreachable. But somehow you don't feel discouraged. You feel invited, challenged. Because while the speed of light may be the universe's hard rule, it never said we couldn't get creative. You stare into the mirror, not the philosophical kind, the literal, slightly foggy one in your spacecraft's sleeping pod. You've been gone a long time, or at least it feels like a long time to you, but outside, in the universe beyond your bubble of motion, a lot more time has passed. You touch your face, same skin, same lines. Your reflection stares back at you, maybe just a little more tired than yesterday, but not older, not really. Meanwhile, back on Earth, your friends, your family, your old school rivals, they've all lived an extra 20 years you didn't. Time dilation isn't just a mathematical footnote anymore. It's personal, it's in your bones. And now you ask the question that's been scratching at the back of your mind since that first interstellar mile. Does time dilation actually slow aging? Short answer, yes. Long answer, let's talk biology. Your body runs on clocks, not just the ticking ones in your gadgets, but the chemical and cellular oscillators inside every organ. Your heart beats, your cells divide, your neurons fire, all on schedules tied to metabolism, circadian rhythms, and environmental cues. But if your entire biological system is moving at relativistic speeds, if your ship is cruising along at, say, 0.9 C, then every tick of your internal clock stretches. To you, it feels normal. But to someone watching from a stationary frame, your biology is running in slow motion. This means fewer heartbeats, fewer breaths, fewer cell divisions per unit of external time. From their perspective, you've simply aged slower. It's not a metaphor. You've actually lived fewer seconds than they have. Historians still argue whether this qualifies as anti-aging. Some call it the purest form of longevity. Time has passed, but you haven't. Others counter that unless you return to society, or unless you experience the years you miss, it's not really life extension, just time deferral. But the physics is clear. If you go fast enough, long enough, you will return biologically younger than the people you left behind. NASA's twin experiment with Scott and Mark Kelly hinted at this, albeit on a microscale. Scott, in orbit for 340 days, came home a fraction of a second younger than his Earthbound brother. Most of the focus was on DNA expression and immune response, but the physics? Quietly smiling in the background. Now, let's imagine an extreme case. You take a one-way trip to a star system 50 light-years away at 99.995% the speed of light. Round trip, it takes you 100 years from Earth point of view, but to you, maybe 5 years pass. You've effectively shaved 95 years off your biological timeline. Your muscles haven't decayed, your skin hasn't wrinkled, your mitochondria have barely noticed. From Earth's frame, you're a miracle of youth. From your frame, it's just a slightly extended vacation, with better views. Of course you can't feel time dilation. There's no tick, no tug, no shiver down the spine. You don't wake up younger. You wake up the same. It's only when you return, when clocks are compared and calendars dusted off, that the truth hits. You skipped time, and time politely let you. Quirky detour. Some biotech enthusiasts have half-jokingly proposed launching future billionaires on high-speed space cruises as a longevity investment. Spend 5 years at 0.999 cents, come back biologically younger than your grandchildren. It's a logistical nightmare, but in theory, plausible. But aging isn't just about clocks, it's about wear and tear. So let's pause and ask, is every aspect of aging slowed by relativistic speed? Cellular aging? Yes. Your cells divide more slowly relative to Earth time. Telomere shortening? Slowed. Oxidative stress and DNA damage? Technically, they still happen, but they're measured in your own stretched out seconds. But there's a big caveat. Radiation. At high speeds, space becomes a bullet storm. The faster you go, the more intense the cosmic rays. And those rays don't care about your slow biological clock. They slam into your body with energy levels that can cause cancer, DNA damage, and more. Time dilation gives you youth, but space tries to steal it back. And your metabolism? That's trickier. Some models suggest that even though time stretches, your biological processes are still running based on internal chemical cues, which means you might not feel any difference. You'll get hungry on a normal schedule, you'll need sleep, you'll get bored. Though maybe that last one speeds up significantly when your only view is the same star field for months. Now imagine this, a society of relativistic travellers, colonists who spend years at high speeds moving between star systems. They age slower than the people who stay behind. Each return trip turns them into time ghosts, physically young but temporally ancient. How would that affect culture, relationships, inheritance laws, fringe idea? There's a theory in speculative biology suggesting that if we ever do create interstellar humans, we'll need to adapt not just to space, but to asymmetric time. Imagine uploading someone's consciousness into a system that can run slow or fast depending on velocity. Your mind, as elastic as space-time itself, sort of like Spotify for existence. Slow it down, speed it up, depending on how fast you're flying. Aging then becomes a choice, or at least something to schedule, but let's come back to you, right now, in your ship, watching the Earth shrink into a memory. Every second you fly, the clocks back home spin faster. Birthdays pass like blinking lights on a distant highway. People grow old. You don't. Or rather, you do, just differently. And someday, maybe decades from now, you'll come back. They'll ask how you stayed so young. And you'll tell them the truth. You didn't slow time. You simply stepped aside and let it rush past. You wake to silence, not the absence of sound, but that heavy cosmic quiet only deep space can provide. No birds, no cars, no keyboards clacking in another room, just the soft thrum of your vessel's systems and the sound of your own breath in your helmet. You stretch. Everything creaks just a bit. It's been weeks since you left Earth, or maybe months, or years. Time has a different flavour out here, faintly metallic, strangely dry. You feel fine. You feel normal. But beneath that calm, something strange is happening. Your body, your entire biology, is quietly adapting to relativistic speed. You're still human. You still crave coffee and dread in boxes, but you're not quite the same creature who stepped aboard. Because high-speed travel doesn't just affect time, it messes with your biology too. Let's take it from the top. Your muscles. The faster you move, the less you feel the strain of gravity, especially if you're cruising in deep space with no planetary pull. That leads to the same problem astronauts face on the International Space Station: muscle atrophy. Without regular resistance, your muscles start to forget their purpose. Legs, back, even your neck. If left untrained, they begin to wither, not instantly, but slowly, methodically. Like a bored teenager deciding gym class is optional. NASA combats this with hours of daily exercise in orbit. but on a relativistic vessel. Multiply that by years. Or worse, imagine years from your perspective while decades pass outside. By the time you return to Earth, gravity might feel like trying to wear an elephant. Next, your bones. They get in on the rebellion too. Without mechanical loading, the stress that comes from standing, walking, jumping, your bones start to lose density. Astronauts can shed 1 to 2% of their bone mass per month in microgravity. The fancy term is disuse osteoporosis. You might call it the skeleton going on vacation. Historians still argue whether early space agencies underestimated the long-term effects of microgravity on the human frame. Some believed the body would just get used to it. Others knew better. The truth turned out to be harsher. The body doesn't adapt, it compromises. But let's not forget the brain. Out here, floating through time-dilated emptiness, your brain becomes your entire world. No sunlight cues, no crowded commutes. Your circadian rhythm starts to drift, desynchronize, to be technical. Sleep gets weird. You nap when you're not tired. You stare at the ceiling, exhausted but wired. Even on Earth, time zones mess with your brain chemistry. Out here, you're in your own private time zone that no one shares. Your memory plays tricks too. Studies on astronauts show that cognitive sharpness can degrade in long-duration missions. Part of it is monotony, part of it is stress, but part of it is something else, neural adaptation. Your brain rewires itself subtly under prolonged isolation, altered schedules and unchanging environments. And let's talk cardiovascular effects. On Earth, your blood has a clear task: fight gravity. It pulls in your legs and feet, and your heart works against that. In 0G or during constant acceleration, blood redistributes. You puff up, your face swells, your legs shrink, your heart doesn't have to work as hard, so it starts to decondition. There are astronauts who come back to Earth unable to stand without fainting. That's from just 6 months. Imagine 6 years, relativistically compressed. Now here's something more speculative but no less intriguing: immune function. It gets weird up here. Some immune cells slow down, others go haywire. Viruses that lie dormant in your body, like herpes or shingles, can reactivate in space. Your immune system is out of its comfort zone. You're not just a time traveler anymore, you're a petri dish. Quirky side note, studies have shown that some bacteria actually become more virulent in microgravity. Not stronger per se, but more aggressive. Scientists aren't exactly sure why. Maybe it's the stress response. Maybe it's the way cells float and interact in different directions. Either way, microbes don't read Einstein, but they thrive in his playground. So how do you combat all this? Artificial gravity helps. Spin your ship like a giant wheel. Centrifugal force gives you that sweet simulated downward pull. You stand, your bones stay dense, your heart keeps pumping. But building that kind of ship is no small task, and at relativistic speeds, even tiny forces feel complicated. The math gets heavy, the hardware heavier. Diet? Sure, nutrients can slow some biological decay, but space messes with appetite, digestion, even taste. Food gets bland, smells don't travel well. Your brain says, "Why eat?" Meanwhile, your muscles whisper, "Why lift?" Fringe proposal. Some have suggested hibernation for long-term space travel. Slow the body's metabolism, cool the core temperature, reduce energy demands, sleep through the years. Let your cells dream at half speed while the universe hurtles by. There's research into torpor states, mostly in animals, but the hope is that one day we'll learn how to pause ourselves. Not for time travel, just for survival. But if you're awake, fully awake, there's a psychological cost too. You age slower, sure, but you feel every minute, every breath, every sigh, every silent meal in the galley. Time isn't just physical, it's emotional. stretching or shrinking, it doesn't erase your boredom, your fear, your loneliness. The body might resist change, but the mind, it starts inventing it. And here's the strangest part. Once you return to Earth, you'll have aged less, but you may feel older. The effort of maintaining your body in space, the strain of altered biology, the weirdness of never quite syncing with Earth time, it all adds up. You are a walking paradox, chronologically young, experientially ancient. So yes, time dilation changes your life, but it doesn't stop it from wearing you down. Historians still argue whether our obsession with relativistic speed blinds us to the messy biological cost. We talk about years gained, but not strength lost, seconds saved, but not identity shifted. Because the truth is, the faster you move, the harder you must fight to stay whole. Time might slow, but entropy never does. So you zip up your suit, strap into the bike, fight to keep your muscles strong, your bones dense, your brain sharp. You take vitamins, cycle routines, and maybe reread the same book for the 100th time. Because when you come back, if you come back, you want to be more than a time traveller. You want to be human. You wake to a glow on your skin. It's soft, ambient. Not the sharp overhead fluorescence of your ship's control panel, but something warmer, rising orange like a sun rising over some distant ocean you've never seen. You blink, stretch, unbuckle. Then you look out the window and you see it. Earth, blue and brilliant, cradled in the black. The curve of the atmosphere shimmers faintly. Cities glitter like neural networks lit by thought. You don't speak. You just float, still inside the ship, barely breathing, knowing that whatever happens next, you're not the same. You've returned. You're home. Only it isn't home, not really. Time has passed here. More time than you've lived. Friends you left behind are older, much older, some gone. Entire decades unfolded while you felt only a few quiet years. The music has changed, the politics, the language maybe. You try to open a social media app and it's like reading hieroglyphs designed by influencers. You're a relic and a marvel all at once, a human time capsule, and now you have to live here. Welcome to the strange possibility of relativistic cities, because let's stretch this out. Not just one astronaut, not just one mission, but whole societies. Ships full of people travelling regularly at high speeds, back and forth, between stars, between colonies, and between frames of reference. It starts as a thought experiment, of course, but the consequences quickly spiral. Imagine this. Earth has established orbiting colonies around distant moons and planets. Some travel in massive generational ships between systems. Others live on worlds close to massive stars where gravity bends time dramatically. Others zip around mining operations at relativistic speeds, barely aging while decades pass for everyone else. In this future, time zones don't just mean you're 3 hours ahead. They mean you live in a different decade. Someone might leave Mars for a supply run to a relativistic station orbiting near a neutron star. The trip takes them 2 subjective months. They return, and 10 years have passed. Their younger sibling is now their older sibling. Their apartment is leased to someone else, their dog has died, been cloned and died again. You see the problem, and it's not theoretical. Even today, astronauts on the ISS experience measurable time differences from US Earth dwellers. We're talking nanoseconds, but scale that up with real speed, real distance, real durations, and suddenly, time isn't something everyone shares anymore. Historians still argue whether time dilation would create entirely separate cultural identities. Imagine a community of workers who live their lives on a ship that runs near light-speed trade loops. Every round trip costs them only 2 years, but Earth moves forward by 40. They keep coming back to different centuries, different tech, different music genres, different slang. How do you maintain identity in that world? You might see the emergence of temporal castes, slow time people and fast time people. Political systems would need to account for citizens who don't age linearly, who can't vote consistently, who disappear and reappear younger than their grandchildren. There would be relativistic contracts. Rent this apartment expires in 2 subjective months, meaning, of course, that you'll be gone for 50 years. The landlord's great-grandkid will be your new neighbour. Quirky idea? A temporal embassy. A neutral space where fast-time travellers and slow-time dwellers can meet. A place with shared calendars, adjustable lighting to simulate both timescales, and AI translators who help bridge not just languages, but decades of context. Your relationships change too. Dating someone from Earth while living in a relativistic city. Good luck. You'll miss every anniversary. They'll age out of your type while you're still in stasis. You could leave for a week, only to return and find they've had a whole life. Married, divorced, raised kids. You missed everything. And what about kids? In a relativistic society, parenthood breaks time. You might leave when your daughter is 10, come back biologically unchanged, and find she's 40. The dynamics shift. The authority evaporates. She becomes your guide, your interpreter for a world that no longer matches your internal clock. You don't even have to leave the solar system for this to start becoming real. Colonies orbiting closer to massive planets, or even living in high-speed ring habitats, would already experience time differently. It's subtle at first, a few seconds, a few minutes, but stack those differences and they become lifetimes. Some might embrace it. There would be fast-time cities and slow-time retreats. People who live fast, travel fast, stay fast, aging slowly while the rest of the galaxy churns forward. Others might choose stability, a home in one time zone, a linear, consistent life, no surprises, but it creates tension. Trade becomes complicated. Communication must be carefully timed. Imagine waiting for a reply to a message you sent, only to receive it from a sender who hasn't sent it yet by their clock. Entire temporal infrastructure systems would have to emerge to handle this. Timestamp correction, relativistic messaging protocols, age verification algorithms that don't just check years, but experience time. There might be relativistic crime too. Imagine disappearing just before sentencing, returning a week later while everyone else served 20 years, or faking alibis using time distortion, or selling temporal displacement tickets on the black market. Miss your mortgage deadline? Just outrun it. And yet, amid the chaos, something beautiful could emerge. A new kind of time consciousness. You'd start asking questions not just like how old are you, but how long have you lived? Not just where are you from, but when did you last check in? Communities wouldn't be based solely on location, but on temporal phase, shared reference frames. You'd choose whether to align with slow time people or spend your life in fast forward. Culture as a function of clocks. Back on your ship, you prepare to land. Earth's pull is stronger now. It's time, heavier. You haven't aged much, but Earth has. Its streets are older, its air different. You step out feeling like a traveller not just through distance, but through generations. A man walks past you on the landing platform. He looks familiar. You realise, with a jolt, he's the grandson of your childhood friend. The one who cried when you left. The one who always said you'd come back too late. And you did. But not because you meant to. Because that's what speed does. It saves your youth, but steals your context. You look back at your ship. You could leave again. Jump forward another 100 years in a blink. You could outrun war, outlive politics, watch civilizations rise and fall like weather. Or you could stay and try to rebuild something in this new Earth. A slow city, a rooted time, a home. You sit alone on a bench made of unfamiliar metal, in a park that didn't exist when you left. There's a tree nearby, its leaves flickering purple in the twilight, its roots woven through artificial soil. Children run past, their laughter universal, timeless, but the language on their tongues is not one you grew up speaking. Your translation implant keeps up, but it's like watching the world from just behind a pane of glass. You've returned to Earth, but the Earth you knew has moved on, and so has everyone you knew. This is the human cost of high-speed travel, not just time dilation, not just relativistic math games, but one-way journeys that leave entire lives behind. Because moving fast enough to stretch time also means moving fast enough to miss it. You remember what it was like, the launch, the confidence, the mission, the promise that you'd only be gone for 5 years, your 5 years. You didn't expect things to stay exactly the same, of course, but you didn't expect to come back and find your family's home turned into a historical landmark, your favourite band reissued as classical pop, your ex married, then remarried, then peacefully retired. They weren't waiting for you, they were living. And so now you face the unspoken truth of time dilation. It's not just a scientific reality, it's an emotional divide. Time tourists. That's what some people call travellers like you. People who come back out of sync, untouched by the years that aged everyone else. People who skipped decades, not by cryogenic sleep or suspended animation, but by moving faster than time could follow. Historians still argue whether the first relativistic travellers, when they do eventually arrive, will be welcomed like astronauts or pitied like ghosts. Will they be heroes or strange reminders of a past that refused to age gracefully? The idea has already started popping up in speculative fiction, in off-world mythology, folk tales of people who leave and return unchanged, watching their descendants grow up and die in what feels like a weekend. These stories are cautionary, not about the dangers of space, but the dangers of disconnection. Because you did everything right, you followed the protocols, you logged your hours, you ran your exercises, you wrote in your shipboard diary faithfully, but none of that prepares you for this, for the way the world politely offers you catch-up sessions. Augmented history feeds, guided reintroduction classes. The relativistic social reintegration office is the warmest bureaucracy you'll ever meet. They offer you therapy, housing credits, and a little handbook titled Your World Now. You read it in silence, but a handbook doesn't help you mourn people who are still alive, just older, changed, happy without you. Some of them try to reconnect. A sister, now 87. She trembles when she hugs you, not from emotion, but from arthritis. She talks about things you weren't there for. Weddings, births, a pet you never met, a heartbreak you never helped mend. You missed it all. And you smile, you nod, you pretend that you're the one who changed. Some don't want to see you at all. A best friend, now bitter. They accuse you of abandoning them. Maybe not in words, but in expressions, in silences, in sideways glances at your still young face. You don't get to say, "I'm sorry" anymore. That currency expired 20 years ago. Quirky story. A relativistic pilot once came back and married his granddaughter's ex-wife. It sparked a debate on ethics, identity, and temporal proximity. But technically, they were the same age. The heart doesn't run on calendars. Neither does love. Or guilt. This is the great irony. While time dilation slows your clock, it doesn't freeze your story. Everyone else keeps writing pages, and when you come back, your chapter is out of sequence. You try to adapt, to find work, but your credentials are outdated. Your fields have merged, mutated, vanished. AI does most of it now. You walk into a job interview and get a polite smile that says, "You're from another century, aren't you?" Some relativistic returnees band together, forming communities where everyone understands what it's like to lose people in real time. They call themselves the Long Travellers. They meet in parks, play ancient music, speak in half-forgotten dialects. But even here, nostalgia carries weight. It becomes its own form of gravity, pulling them backward. Others choose to leave again. They board ships, faster now, quieter, more efficient. They skip forward another 50 years, hoping that the world will be easier the next time around. It rarely is. Time doesn't heal what it doesn't remember. And then there are those who become teachers, story keepers, living fossils of a slower past. They lecture in classrooms full of students who can't imagine a world without neural uplinks or Mars commutes, but they listen. They ask what it was like to walk under trees that grew naturally, not engineered to bloom on schedule. They marvel at your face so unchanged. You laugh, but it aches. Fringe movement. Stay time. A cultural philosophy that promotes never leaving your native time frame. It's not anti-science, it's anti-isolation. Life is not a speed run, their slogan says. Live in your moment. They write poetry that's heavy with resentment toward relativistic explorers. Some call them Luddites, others call them the only ones who remember how to stay. So what about you? You sit on the bench. The sky above is an unfamiliar shade of green, climate adaptation tech. There's a soft hum from a distant drone. You pull up the planetary clock on your wrist. Earth standard date, 2175. You left in 2126. You've been gone 49 years. To you it was 7. The math was elegant. The physics was precise. But nothing in Einstein's equations warned you about this kind of loneliness. You rise, walk slowly through the city. It's clean, safe, automated. But every doorway, every billboard, every street musician playing a remix of a song you loved reminds you that this isn't your time. And yet, there's beauty here too. New constellations in the sky. Art installations made of projected fog, children who have never known war, a stranger who smiles at you and offers directions without judgment. You've landed in the future, uninvited but not unwelcome. You may not belong here, but you're here, alive, still young in a world grown old, and somewhere deep inside you know that this moment, right now, is the one where your second life begins. You're standing in a suit that hums faintly, sealed against the void. It's not fashionable, but it's the only thing between you and a death you'd never even feel coming. Behind you, the spacecraft shimmers under distant starlight. Ahead, nothing but black. You're in deep space now. No orbit, no planetary pull, just velocity and emptiness. And something invisible, yet lethal, is dancing all around you. Cosmic rays, they don't sparkle, they don't hiss, they don't even knock politely before slipping through your body like ghost bullets. Most of the time you don't notice, but they're there, streaking through your cells, cracking DNA strands, sometimes splitting atoms in your bones. It's not personal, it's just physics. And as it turns out, the faster you move, the worse it gets. Time dilation might stretch your seconds, it might slow your aging, but it also means you're moving into more danger, faster than your ship's shielding can handle. Welcome to the uncomfortable truth. High-speed travel through space isn't just hard on your social life, it's hard on your health. Let's start with the basics. Cosmic rays are high-energy particles, mostly protons, accelerated to near-light speeds by supernova, black holes, and other cosmic drama. When these particles hit Earth's atmosphere, they explode into showers of secondary particles, like the Muons we met earlier. But out here, with no atmosphere to protect you, those particles slam straight into you. At Earth speeds, it's a slow drizzle. At relativistic speeds, it's a sandblaster. Because as you move faster, the particles you encounter aren't just standing still. From your perspective, the interstellar medium, the background haze of hydrogen, helium and dust, starts to blue shift. The faster you go, the more energetic everything becomes. That innocent hydrogen atom, it becomes a mini meteor. The higher your speed, the more energy these tiny bullets carry, and the deeper they penetrate into your tissues. Time slows down for you. But radiation, it picks up speed. Historians still argue whether early space travel advocates fully accounted for this. In the 20th and 21st centuries, radiation exposure was already one of the biggest hurdles for long-term space missions. Mars crews were expected to accumulate a lifetime's worth of exposure in just a few years, but that's nothing compared to what relativistic travellers would face. This is the speed of death problem. The closer you get to light speed, the harder the universe hits back. Shielding can help. Layers of water, polyethylene, magnetic fields. But those only go so far. Every additional layer adds mass, and mass slows you down. It's a cruel trade-off. Protection versus propulsion. Quirky side note, some engineers have proposed building spacecraft with active plasma shields, modelled after the Earth's magnetosphere. In theory, you generate a magnetic bubble around your ship to deflect charged particles. In practice, still science fiction. The power demands alone would fry your budget before you left the launch pad, so you compromise. You plot routes that avoid high-density regions. You sleep behind the most heavily shielded walls. You carry DNA repair meds that are still in clinical trials, and you hope. Because the damage is slow, cumulative, subtle. Maybe it starts with nausea, or headaches, or small lapses in memory. Your body tries to keep up. Your cells patch themselves. Your systems adapt. But radiation is patient. It waits. It builds. It carves into the future you thought you had. Here's the cruel irony. The faster you go to escape time, the more dangerous your journey becomes. Speed slows aging, but amplifies exposure. At 0.5 cents, the damage is manageable. At 0.9 cents, it's severe. Past 0.99 cents, you're basically flying through a sandstorm of subatomic shrapnel. Fringe theory alert. Some researchers suggest that quantum tunneling effects might offer new ways to predict or even phase through certain radiation types. The idea is that at extreme velocities, particles might interact differently, perhaps even allowing shielding tech to behave more like a waveguide, directing radiation away rather than absorbing it. It's promising, also completely untested. Meanwhile, back in reality, even today's astronauts return from orbit with altered chromosomes, weakened immune systems, and early signs of cataracts. That's after months in low Earth orbit. Your journey at relativistic speeds? Multiply that damage exponentially. But that doesn't stop people from trying. In future mission logs, you read entries like, minor flare detected, crew rotated to sleep pods. Dose monitoring threshold exceeded for second officer, pulling from EVA schedule. Hull particle impacts increasing, updating shielding matrix algorithm. People survive, some even thrive, but they age strangely, unevenly, internally. Which brings us to the concept of temporal radiation load, a proposed unit of measurement that combines time dilation and radiation exposure into one efficiency metric. Because what's the point of shaving off 30 years of biological age if you come home riddled with precancerous mutations? It's become a balancing act. You can skip ahead in time, sure, but you have to pay the toll, a few decades younger, a few million extra grey cells, some permanent DNA scars, one long, quiet ride, and maybe the price is your body's ability to replicate itself without error. You look out the window again. There's a glimmer ahead, a nebula, bright and impossible, rippling across your field of view. It's beautiful. It's deadly. You know that even now, photons that started their journey 1,000 years ago are finally hitting your faceplate. And you wonder, not for the first time, if it was worth it. Was it worth the silence, the solitude, the strange decay, the knowledge that your body is surviving in borrowed time, streaking through space like a candle in the wind, slowed by motion but worn by light? There's no easy answer. Some say yes. They say this is the price of discovery, that pushing boundaries means accepting risks, that radiation is just another form of time, carving its marks into your story. Others say no, that time travel without the ability to return whole isn't travel, It's abandonment. And you don't know yet, but you do know this. Time dilation might keep your clock from ticking, but nothing stops the universe from knocking. You sit in the dark, looking at a photograph that wasn't taken yet. It's there, framed, slightly curled at the edges, its surface catching the low amber light of your quarters. You swear you've seen it before. That moment, that place, that person. But it doesn't make sense. The picture's timestamp is a month from now. You check again and again. It hasn't changed. Your mind wrestles with it. Maybe it's a glitch. Maybe the onboard AI preloaded a projection. Maybe you dreamed it, convinced yourself it was real. But part of you, the part that remembers things you shouldn't, keeps whispering, no, you were there. You wonder, is it possible to remember tomorrow? Welcome to the strangest alley of time dilation. Not just the warping of seconds and aging, but the murky question of temporal perception. If time isn't fixed, if it bends and stretches depending on your speed or gravity, then what does that mean for consciousness, for memory, for causality itself? Because physics tells us that time is relative, that much we've accepted, but your brain, your thoughts, they run on a schedule too. Neurons firing, synapses connecting, electrical pulses marking moments, all ticking along a biological metronome. But what if that rhythm isn't as fixed as we thought? Let's explore. Under Einstein's theory, time is another dimension, one you move through whether you like it or not. You don't get to sit still. Even at rest, you're hurtling through time at 1 second per second. The same way you move through space, you move through time. But unlike the other 3 dimensions, we only perceive time in one direction. Forward. Always forward. Never looping, never pausing, never rewinding. That's the arrow of time. But it's not a physical law. It's an observation, a tendency, entropy. The gradual increase of disorder in a closed system gives us that arrow. A broken egg doesn't unbreak. A song doesn't unplay. And yet, special relativity says that from the right point of view, past, present and future all coexist. What looks like the future to you could be the present to someone else. The past could be just around the corner. Time becomes a landscape, not a river. So the question becomes, if time is a place, can you ever remember a part of it you haven't visited yet? Historians still argue whether Einstein himself believed the future was already real. He famously said that the distinction between past, present and future is only a stubbornly persistent illusion. Some physicists have run with that idea, creating models where all of time exists at once, what's called the block universe. In a block universe, time is like a film reel. Every frame exists, even if you're only watching one right now. From this view, now is subjective. It depends on your motion, your position, your frame of reference. And if every moment already exists, what's stopping your brain from brushing against another frame? This is where things get fuzzy, speculative, fringe. Some theorists, especially those swimming near the shores of quantum mechanics, have proposed that consciousness might not be tied strictly to a single temporal direction. That under certain conditions you might experience leakage from future events, a form of reverse causality, or at least a perceptual smudge. There have been studies, controversial, hotly debated, that suggest humans might sometimes react to stimuli before they happen. Tests where heart rate and brain activity spike seconds before a randomly selected image is shown. Pure coincidence? Statistical fluke? Or is your brain peaking at the next frame before the projector gets there? Fringe science? Yes, but not entirely dismissed. Quantum physicist Yakir Aharonov proposed a model in which particles are influenced not just by past conditions, but also future boundary conditions. Called the two-state vector formalism, it suggests that what happens now is guided by both the past and the future. Imagine that. The decisions you make aren't just echoes of what came before, but whispers of what's to come. Quirky detail. In some ancient cultures, time wasn't seen as linear at all. The Hopi people, for instance, had no grammatical tense for future, as we understand it. Their language treats time as a landscape. Events are either manifest, knowable, or unmanifest, not yet observed. But that doesn't mean they don't exist. Sounds a little like relativity, doesn't it? So back to you staring at that photograph. Is it déjà vu? False memory? A glitch in the log? Or is your mind reacting to a real moment? A frame of time your consciousness skimmed before returning to now? Because time dilation doesn't just affect physical objects. It affects your perception of sequence. The longer you live in a frame of time separate from everyone else, the more your memories start to drift. What's past for them may still be future for you. You could meet someone who remembers something that, for you, hasn't happened yet. What happens when you compare notes? Some travellers report dreams of places they swear they hadn't visited yet until they do. Others claim to remember the end of missions they're still halfway through. It could be stress, isolation, or it could be the mind learning to exist in non-linear memory. It might sound ridiculous, but ask a quantum computer how it feels about time. Ask a photon whether it experiences distance. Ask a muon falling through the atmosphere whether it believes in death. Reality is weird. So is your brain. And now you're wondering, if time is a dimension, could you learn to navigate it? Not with ships or engines, but with awareness. Could you train your mind to notice when moments don't add up? To sense when your path through time has taken a curve? That's not science yet, it's speculation. But so was time dilation once. So was GPS. So was flying. Maybe you can remember tomorrow, maybe not as an image but as a feeling, a subtle alignment, a shadow of something waiting. You set the photo down. It still hasn't changed, and tomorrow is still coming. You reach for your watch, not the sleek digital band that syncs with satellites, not the clunky analog kind either. This one's different. Smaller, stranger, a prototype, a gift from someone you met long after you were supposed to meet them. It doesn't tell you the time, it tells you a time. One you're still learning how to read. This is a quantum clock, and it doesn't tick like anything you've used before. You already know time can stretch, bend, and slow, depending on how fast you move or how close you are to something massive. Einstein carved that into the physics books. But now, you're looking at something even stranger. Time, not just as a dimension, but as something that can get fuzzy at the smallest scales. Welcome to the world of quantum timekeeping, where seconds aren't smooth, and the tiniest fractions of a moment can slip through your fingers like water. Let's start with basics. Atomic clocks, the gold standard for measuring time, work by counting the oscillations of atoms, usually cesium. These atoms tick billions of times per second. By counting those ticks, we build our definition of a second. But quantum physicists weren't content with just billions. They wanted more. Enter optical lattice clocks and single ion clocks. These newer designs can detect the passage of time with attosecond precision. That's 1 quintillionth of a second, far beyond anything you or I can feel, but absolutely critical when you're navigating space, syncing GPS, or trying to compare clocks in 2 different gravitational fields. So why go that small? Because time, it turns out, isn't quite so tidy down there. At quantum scales, everything is uncertain. Particles don't have clear positions or velocities. They exist in probabilities, clouds of maybe. And time becomes less of a marching drumbeat and more of a jittering whisper. It doesn't flow, it flickers. And that means even timekeeping, one of the most fundamental human activities, isn't immune to quantum weirdness. Fringe concept? Some researchers propose that time itself may be emergent, not a fundamental property of the universe, but something that arises from entanglement and the relationships between quantum systems, meaning Without change, without interaction, time might not even exist. Yeah, sleep tight with that one. Historians still argue whether Einstein would have embraced this idea or scoffed at it. He famously resisted quantum mechanics, calling it spooky and refusing to believe that God plays dice with the universe. But the irony is, quantum theory has become the key to understanding time at the smallest, sharpest levels. Let's look at the experimental side. In 2020, scientists managed to build a quantum clock so sensitive that it could detect the difference in time between two locations only a millimeter apart, just from a slight difference in gravitational potential. A millimeter. Think about that. You and your friend could be standing in the same room, one of you wearing shoes, the other barefoot, and your clocks would technically tick at different speeds. That's how sensitive time really is. And quantum clocks don't just measure time, they challenge our idea of what time is. In quantum mechanics, we talk about superposition, the idea that particles can exist in multiple states at once until observed. Some researchers now wonder, could time itself exist in a superposition? In other words, could a system exist in two different times simultaneously? It sounds ridiculous. But certain experiments, like the quantum switch, where two operations are performed in an order that's not fixed, hint that time may not be a straight line. In some systems, the order of events becomes ambiguous. Cause and effect get blurry. What came first doesn't matter. In a quantum sense, they happen together, or in reverse, or not at all. Quirky proposal. In 2022, a team proposed using entangled clocks to test the possibility of indefinite causal order. If successful, it would mean that in some quantum systems, the very structure of time, before, during, after, could collapse. And you're thinking, okay, but what does this mean for me? Well, if you're moving at relativistic speeds, your sense of time is already detached from the universes. Add quantum clocks into the mix, and suddenly you're dealing with multiple valid timelines, some of which don't even agree on when things happened. Now imagine trying to sync with someone else's ship, or deliver a package from Earth to a space station orbiting a neutron star, or even send a message across entangled quantum relays. If time itself is uncertain, how do you measure delay, arrival, confirmation? You don't. You start using probability curves instead of schedules. You define events not by when they happened, but by likelihood. And quantum clocks, they become your translator, your interpreter, your fuzzy, flickering friend who whispers, "It probably happened, about now." There's even talk of creating a quantum internet where information can be shared securely and instantly, kind of, between vast distances using entanglement. But to make it work, every node, every satellite, every terminal, every consciousness would need a clock that functions at quantum scale, not to measure when things happen, but to agree on when anything exists. That's where your little device comes in. Your quantum clock doesn't show seconds, it shows waveforms, peaks and troughs of probability. It doesn't tick forward, it wavers, and somehow you've started to understand it. You can feel when events are converging. You can tell when something's about to happen, not because you saw the schedule, but because you've learned to read the statistical rhythm of space-time. Some say that's nonsense. Others say you're just ahead of the curve. Maybe someday we'll abandon mechanical clocks entirely. No more minutes, no more days, just quantum signatures, vibrations that match your motion, your frame, your reality. Because time in the end may not be what we thought. It's not a ruler, it's a shimmer, a flicker in the dark, and you're learning to read it. You sit cross-legged in the quiet of your ship, a mug of something warm cradled in your hands, not because you're cold, but because you need an anchor, a ritual, a small habit that reminds you of yourself. The stars spin silently outside your window, but you don't look up. You're thinking about who you are, and more importantly, when. Because the further you drift from Earth, The longer you live outside its clock, the more you begin to wonder, are you still you if your timeline no longer matches anyone else's? Time dilation isn't just a physical shift, it's psychological, a warping not just of seconds and heartbeats, but of identity. The longer you move fast, the more you slip, not just into the future, but out of alignment with everything and everyone you ever knew. At first, it was manageable. You still recognized the world through transmissions, news feeds, culture updates, the occasional music drop. But now even language sounds different. Slang has evolved, voices have changed, technology has leapt beyond your training manuals. The food looks synthetic, the interface is unfamiliar, people speak faster, or maybe your brain just runs slower in comparison now. You're not out of touch, you're out of phase. This is the psychological cost of time drift, and it's deeper than loneliness. It's the realization that while you were busy not aging, everyone else was changing without you. That even the concept of now is something you no longer share with anyone else. Historians still argue whether early relativistic experiments considered the mental health consequences of time separation. Haffel and Keating didn't lose decades in their atomic clock flights, but their successors might. This science accounted for seconds. It didn't account for detachment. Let's be blunt. Humans are social creatures. We define ourselves by shared experience, shared seasons, shared cultural touchstones, a song on the radio, a shared reaction to a solar eclipse, a holiday at the same time every year. But if you're on a relativistic trajectory, none of that matches anymore. You hear a song that just came out. But back on Earth, it's already nostalgic, a throwback. You think about someone you knew in your youth. You look them up. They died 20 years ago, surrounded by family. Their obituary lists children you never met and a life you weren't part of. You reach out to their grandchild, who answers your message cautiously, as if you're some myth they weren't sure was real. You realize the last person who understood your timeline died before your return was even announced. And what happens to a mind when it lives this way? Constantly disoriented, displaced. Quirky study. Early AI simulators once attempted to mimic the experience of time drift by feeding test subjects a deliberately accelerated culture stream. 10 years of media, language, and news in a few weeks. Some participants adapted quickly, others became withdrawn. They struggled to connect to what they were seeing. One subject described the feeling as walking through someone else's dream. That's what you live with now, every day, dreamlike dissonance. It's subtle at first. You forget how to make small talk. You can't follow a joke. The references mean nothing. People nod politely at your stories, then move on. You were the future once. Now, you're an echo. Even your memories betray you. You remember your sister at age 25, the smell of her cooking, the sound of her laugh. But she's gone now, replaced by a video message from a woman in her 60s who still calls you by your childhood nickname, but whose eyes are older than your own. You can't reconcile it. You say her name out loud, hoping your voice will match the moment. It doesn't. And what about yourself? You feel younger than people born after you. You walk differently, think differently. You still double-check systems no one uses anymore. You still reference celebrities who've long been memes. You still dream in Earth Standard Time even though your ship runs on Martian UTC. Your ship's AI tries to help. It offers context prompts, emotional check-ins, memory stabilization exercises, but it doesn't understand because it didn't leave anyone behind. You did. Some travelers cope by building routines, meditation, journals, rituals. One person famously recorded a daily video addressed to their past self, like a time capsule in reverse, trying to keep their own personality intact. Others fall into what's now called chronoshock, a term coined for the psychological condition experienced by returning relativistic travelers. Symptoms range from mild derealization to full-on identity collapse. The most severe cases involve people who refuse to accept the current year, insisting they're still in the timeline they departed from. And yet a few thrive. They become teachers, artists, guides to others entering this strange non-linear life. They write manifestos about temporal fluidity, the idea that identity is no longer fixed to a single historical line, but something that drifts like a cloud across multiple presents. They form communities, not based on location, but on temporal proximity. People who've experienced similar dilation levels. They understand each other's pacing. They finish each other's references. They exist in a bubble of relative sanity, while the rest of the world spins past. Fringe philosophical debate. Are relativistic travellers more human or less? Some argue that they've seen what time really is, that they've lived in slowed hours, seen centuries fly by, and returned with minds sharpened by patience. Others argue that they've lost something essential, the ability to share time, because if no one else is keeping pace with you, what does your story even mean? Are you still the protagonist? Or just a side character in someone else's future? These are questions your ship can't answer. Your tech can't solve them. Not even your quantum clock with all its precision can tell you who you are when everyone else has rewritten the timeline without you. But maybe you don't need the answers yet. Maybe it's enough for now to take another sip from your mug, to listen to your heartbeat, to record your thoughts, however disjointed they feel. Because even if you're out of sync, you're still here. Still thinking, still wondering, still watching time pass. Not as something you've lost, but as something you can still choose to shape. And that in itself is a kind of anchor. You open a drawer lined with velvet and chrome. Inside, nestled in soft foam, are things that look like medical tools, flash drives, and maybe, if you're honest, a few items straight out of a science fiction collector's shelf. One glows faintly, another hums when you pick it up. This is your temporal insurance kit, because you're not just hoping to survive time drift anymore, you're trying to cheat it. Let's be clear, you can't stop time, you can't rewind it, but if you're clever and very, very rich, you might just hack it. These are the tools people are starting to use to fight back against the tyranny of time, not with speed, not with math, but with tech. Welcome to the strange, increasingly plausible world of temporal cheating. Let's start with the oldest dream, cryonics. It's simple in theory. When your body can't be saved, it's frozen, not just cooled but vitrified, turned into a glass-like state where no cellular decay can occur. You're suspended in time, like a paused video, until the future figures out how to restart you. It's not just pulp fiction anymore. Dozens of facilities already exist. Liquid nitrogen chambers, biostasis protocols, legal grey areas that give lawyers headaches. Thousands of people have signed up, many already on ice, waiting for a century that might want them back. Historians still argue whether the first cryopreserved bodies were frozen too late to be viable. But modern practitioners insist the science is improving. Better vitrification, less ice crystal damage, more control over neural preservation. Still, no one's ever been revived. So far, it's a one-way bet. Quirky footnote: there's a growing community of neurocrionicists, people who skip the full-body route and choose only to preserve the brain. The theory? If all your identity lives in the brain, why pay for the torso? The body's replaceable. The self is not, but cryonics is passive. What about active cheating? Enter mind uploading. The idea: scan a brain in high resolution, map every synapse, and recreate that structure digitally. Not a recording, a continuation. You in code. Maybe not in a robot, maybe not in a simulation, but somewhere. That you could exist forever. Or at least until the data degrades. And that's where it gets interesting. Because a digital you doesn't age, doesn't breathe, doesn't metabolize. You could pause yourself, run on slow mode, hibernate for decades, then wake up for the highlights. Presidential elections, alien contact, concerts that only happen every 500 years. Some futurists call this stutter living. Instead of riding time like a horse, you skip across it like a stone, 1 decade awake, 10 asleep, leapfrog into the future with barely a wrinkle. But there's a catch. There's always a catch. No one knows if a digital consciousness is you or just a convincing copy. You upload your brain, but do you go along for the ride? Or is the real you left behind, blinking, wondering why the upload smiles just like you do? Fringe debate. Some neuroscientists suggest that continuity of consciousness might not be necessary for identity. That if a future version of you remembers your past, feels your feelings, makes decisions you would have made, that's close enough. Others say, close only counts in horseshoes and holograms. Still, the tech is progressing. Brain scanning resolution is improving. Memory mapping is moving out of mouse models and into primates. AI is helping decode mental patterns in ways that seemed impossible a decade ago. And for those unwilling to wait, there's memory archiving. A softer cheat. You don't upload yourself, just your experiences. Daily memory syncs, sentiment logs, emotion charts, all stored in protected archives. When your future descendants activate the files, they don't meet you, but they hear your thoughts, read your dreams, learn who you were, time travel by memoir. But maybe you want something more tactile, more now. There are rumours, technically classified, of neurological slow-motion implants, brain-computer interfaces designed to stretch perception of time during high-speed missions. Not actual dilation, but a simulated mental slowdown. So even a 5-minute decision window feels like an hour. The line between time dilation and time hallucination gets very thin. Early prototypes gave pilots severe nausea, later ones smooth as silk, and then there's chronocognitive buffering, a technique in its infancy. The goal? To insulate your perception of time from the world's. You'd experience a stable subjective pace, even if years whip past in the real world. Useful if you're spending long periods near relativistic environments, or trying to stay sane when your ship's clocks tick out of sync with Earth. Imagine living in a shell where every second feels normal, no matter how the outside universe warps around you, like an emotional gravity suit. But let's not forget the biological angle. Gene therapy and nanomedicine are quietly racing to slow aging at the source. Telomere extension, cellular repair, senescence reversal. Some researchers claim early trials have already doubled the lifespan of lab rats. Others suggest the first human to live to 150 has already been born. When combined with time dilation, you'd have a biological plus relativistic longevity cocktail. Travel near light speed, age at half the normal rate, and do it in a body that only shows wear every 200 years. It's a future where time cheating becomes not only possible, but expected. Fringe whisper, chrono elites, wealthy individuals quietly building private fleets for relativistic escape. Not for exploration, but to jump forward in time, invest in the stock market, sleep through recessions, wake up in utopias, or at least better Wi-Fi. It's not science fiction anymore, it's just poorly disclosed science, so you close the drawer, you don't know if you'll use the implant, or the archive drive, or the backup serum still blinking blue, but just knowing they're there, it makes the future feel a little less heavy. You may not be able to outrun time, but you can negotiate with it. Trade seconds for stories, years for meaning, sleep through the worst, wake for the wonder, and maybe, just maybe, learn to live on your own terms. You step outside, not onto Earth, not onto Mars, not even onto a spaceship dock. You're standing on the observation deck of a station so far out it no longer orbits anything with a name. There's no sunrise here, no planetary horizon, just the endless quilt of stars, some brighter than others, a few already burned out, but their light still making the trip. You breathe in recycled air, feel the faint vibration of artificial gravity beneath your boots, and stare into the black. And then it hits you. Maybe for the first time in full, you made it. Not just to another place, but to another when. You have become something strange, something no human was ever supposed to be. You've carved your way through time like a comet, flashing fast and alone through stillness. And now, at the far end of this journey, you ask the question that's been waiting since section 1. What happens when you come back? Not physically. You've done that. You've touched down, made calls, eaten real food again. Watched the world blink in confusion at your unchanged face. No, what happens when you come back to time? When you finally choose to stop running? That's the true end of any relativistic adventure. Not the moment you land, but the moment you decide to let the universe catch up. Because even now, you could leave again. You have the ship, the knowledge. You could shave off another 100 years in a blink. Time is still cheatable, and you're still very, very good at cheating it. But you're tired. Tired of being the ghost in someone else's future. Tired of missing things you didn't even know to miss. Tired of people marveling at how young you look when inside. You feel 1,000 years old. You want to live again, in real time, in sync. But how? Historians still argue whether returning relativistic travellers ever truly reintegrated. Some claim they became wandering sages, trapped between centuries, offering advice and caution. Others say they vanished quietly, living simple lives far from public view. You don't know which you'll be yet. But you do know one thing: the physics will never stop. The universe will continue to obey its rules. Clocks will still disagree, speed will still bend time, and someone, somewhere, will always be tempted to outrun the present. You can't change that, but maybe, just maybe, you can change how we understand it. Because you've lived in the dilation. You've felt seconds stretch into hours, and years compress into minutes. You've watched your timeline peel away from everyone else's like paint from an old wall. You know the cost, the beauty, the ache, and now you can teach it. Not in classrooms, though maybe that too, but in how you live, slowly, honestly. With the understanding that time isn't a line or a trap or a ladder to climb. It's a conversation between where you are and where you've been, between the now you chose and the then you skipped. Maybe you host gatherings, small ones at first, for others like you. A pilot who missed their daughter's childhood. A miner who left Earth during a civil war and returned to peace. A researcher who watched their mentor grow old over transmission windows then disappear mid-message. You don't need to fix them, you just let them sit in the silence with you. Maybe there's coffee, maybe there's music from 3 centuries ago. Maybe someone cries. You start to collect stories, not just your own, everyone's. You build an archive of temporally displaced lives, people the universe swept forward like leaves on a current. You make it public, you make it searchable, and someday, a child whose parent is off-world on a relativistic path finds it and understands. They haven't abandoned me, they just live at a different pace. Time becomes language, and you, finally, can speak it fluently. Fringe idea. Some people begin treating time dilation as a spiritual journey. They meditate on its lessons, let go of the obsession with constant progress. They stop racing the clock. They ask questions like, what would I do if I had all the time in the world? And then they do it, slowly. You write a book. Or maybe you don't. Maybe you dictate it into a handheld device that formats your thoughts into something poetic, because the tech has finally caught up to your words. You call it something modest, like living between seconds. It spreads, because it speaks to everyone, whether they've been on a ship or not. Because deep down we all feel the drag of time, the pressure to move faster, to age slower, to squeeze more into every breath. But you've done that. You moved faster than light's permission slip. You slowed time until it broke around you like glass, and you came back. The clock on the wall ticks. You let it. A friend waves. You wave back. You feel the moment, not as something to outrun or measure or hack, but as something to be inside, like weather, like heartbeat, like home.